All right, I think the book gets a little carried away with this one on how hard it is. Let me go yellow, see if that works here. We know there's going to be a vector going away from this plus up here. And we know there's going to be a vector going towards, and they're going to be equal magnitudes, even though I missed a little with my drawing. And then if I add this vector, let's add the tip to tail, my resultant should be this blue line right there, so straight down after I add my vectors. So it's going to be along the negative y-axis. How do I know that? All these sides of the triangle are the same, so it's going to be a 45-degree angle. That's how I can do that. If they weren't, all these sides weren't the same, I couldn't do that. I'd have to do all the x's, all the y's. This would be a pain. So now I think they want some numbers. We know the strength of one of the sides of the triangle. We could go E equals K Q over R squared. 9.0 times 10 to the ninth Newton times meter squared over Coulomb squared. And I should have not written that there, but I did. And it doesn't matter which one we do, they have the same number. This opposite 1.0 times 10 to the negative ninth coulombs, and that whole thing is over 0.05 squared plus 0.05 squared. I don't have to square root answer because it's squared, right? It's squared. And you throw that in your calculator and you should get 1800 Newton per Coulomb. I'm pretty sure I can assume this is a right triangle, and I'm trying to find the hypotenuse. So it's going to be this squared plus another side of the same squared, and I'm going to square root answer, and I'm going to get about 2,500 Newton per Coulomb. I think my calculator gave me 2545, but significant figures takes it there. That would be my blue side of this triangle up there when I assume that's a right triangle, which I think I can because they're both 45 degrees. 45 and 45 is 90. I do remember geometry a little bit. That one was fun, wasn't it? Fun with a capital PH, just like physics. Bye-bye.